One of the most remote places on our planet is the deep ocean. Yet the movements of water, the currents in the dark depths, affect the water and air that meet on the surface of the sea. The interplay of water and air over thousands of miles of ocean affect weather, climate, life on Earth. The motions of deep water also affect the wastes that are dispersed in the open ocean, and the whole cycle of life, the migrations and habits of marine creatures in the sea. This is the story of a search for a turbulent ocean force. Call it a deep sea storm, call it an eddy, that could dominate the ocean currents. To try to find an eddy in a major experiment as part of the International Decade of Ocean Exploration, a group of oceanographers assembled a fleet of 6 research vessels.
Starboard 20.
Starboard 20, sir.
Half speed.
Half speed.
Keep a sharp watch for it now.
Roger.
Speed down. Dead slow. Eddie, we're coming up with a course change.
Very good, sir.
Put her in the hand steering.
And stern, sir.
The ships carried a variety of ingenious new instruments that could measure the flow of deep water. All the instruments were to be placed in the same piece of ocean at the same time in search of a storm in the sea, an eddy. Oceanographers have in the past gone off to explore the ocean currents in different parts of the world in their own time. Bill Richardson has conducted his own experiments in many parts of the world, recently dropping deep water probes from an airplane along the coast of Florida. Bob Heinmiller is in charge of launching a complex large array of moored current meters. He has launched arrays of instruments in the equatorial Pacific, the Denmark Straits, the Western Mediterranean, Caribbean, and off the coast of Africa.
This is the first time that I've set out on an oceanographic cruise, or on any cruise for that matter. My role in this project is a theoretician. That's someone who tries to do science with a pencil and paper or a computer, not by going to sea. Now, I'd like to learn about the other side and take some measurements myself.
Alan Robinson has experimented at sea in many places, but he is also a theoretician. He prefers not to be tied to any one instrument or theory, but rather to use any new technique or idea that will help to find and understand eddies in any part of the deep sea. Henry Stommel says that he's not an awfully adventuresome type of person who gets a great deal of pleasure out of going to sea. But he has explored currents in the Atlantic, Pacific, Indian Oceans, and many other places. He's been elected to tell this story about a group of very different oceanographers who have measured ocean currents all over the world, trying to find an eddy in one piece of ocean together.
We, a group of oceanographers from a dozen or more universities in the United States and the United Kingdom, have joined together in an experiment that we call the Mid-Ocean Dynamics Experiment, or simply MODE. Each of us has a different approach to oceanography, different instruments, skills. We're independent people, anxious to protect our individuality and freedoms. We're not sure we like this kind of big science. We're not used to it. But we are faced with a number of very big problems. How do the oceans move, and what drives them? We'll try to tell this story from the beginning as it happened. But perhaps, first, we ought to go back some time earlier. Once, a long time ago, it was believed that ocean currents were driven by sea monsters and gods that had the power to drive the warm equatorial water up to the cold Arctic, or to drive the seas eastward or westward on other long journeys of thousands of miles. Today we understand that the atmosphere drives the ocean, and that in turn it receives energy back from the ocean. We know that the surface of the North Atlantic is driven mainly by the winds. The slow, broad movements of large masses of water are broken only by the strong, rapid northward flow of the Gulf Stream. But how does the water below the surface move, and how is it driven? Based on temperature readings, we now suspect that the lower layers move in an opposite direction to the surface flow, affected mainly by temperature differences. This is the large picture. What might one expect in any given small region of the ocean? A slow, uniform current, driven by very gradual temperature differences, so slow that it might take months or even years to detect any motion. But the currents in the deep ocean had never been measured directly. In 1959, the Aries, from Woods Hole, set sail to try out a new tool for measuring the deep currents. John Swallow, a British oceanographer, had aboard some new aluminum tubes that he had designed to float in deep water at fixed depths and to give off sound signals that could be followed by the ship. Swallow supposed that the Aries, though it made only 6 miles per hour and had to make frequent trips back for supplies, could easily keep up with a cluster of 6 of the floats for long periods of time, as they supposedly inched their way along together in the deep ocean. But to everyone's surprise, the floats seemed to be moving neither slowly nor uniformly. Instead, they moved at speeds 10 times faster than expected and in random fashion. What were the forces driving the water in this rapid, irregular way? The Aries soon had to abandon the unequal chase, but fascinating questions had been raised. Are there storms or weather systems, eddies, in this as well as in other parts of the deep ocean? If there are, then how large are they? How strong, and how shall we go about finding them? The place we went to for guidance in our ocean research was, surprisingly, the National Center for Atmospheric Research in the mountains of Colorado. The large computer normally used for studies of atmospheric turbulence was put to work to produce theoretical eddies in the ocean. A number of meetings were held by a theoretical panel of MODE. Alan Robinson, who was at most of these meetings, can describe them.
Overloading the computers.
We spent a number of weeks trying to decide how ocean storms might be made by winds, by temperature differences, and by mountains on the sea bottom. Similar factors can produce atmospheric storms. And then we tried to decide how these theoretical eddies might help us to set up an experiment in which we could get at the real eddies in the open ocean.
And so what is the experiment really going to tell us?
All right. There's 2 questions. One is, can our study of these mechanisms, to what extent can our study of these mechanisms now let us think more rationally about the design of the experiment, the actual laying out of the array?
Sure.
And can, when we do that, get an array which is going to allow us to determine the local dynamics of the eddies themselves. Not where they come from, but the
what's going on?
forces which
Okay. In other words,
right, what's going on right there.
Okay.
And how they're hanging together.
All right.
Right now.
Yeah.
So that we can actually follow this sort of drunkard's walk that the water takes around the ocean.
Yeah.
It's really, we're dealing with a very ponderous thing, aren't we? If we were meteorologists, we could look at the mean circulation of the atmosphere in a few days.
Yeah.
We could follow balloons around, but to do this study for the ocean and these very gradual drifts of the abyssal waters, we may all be retired before something's happened.
Yeah, but I mean, the atmosphere is very helpful because we think that the basic forces in the atmosphere are really rather similar to those in the ocean.
But we also know that the flow in the atmosphere is interrupted and dominated by local storms or weather systems. Where are the storms of the deep sea? Where do we plant an array of instruments to find them? The MODE Executive Committee held meetings to discuss that question.
It seems to me that the single most important question is whether it's going to be over the rough, typically rough, topography or over the smooth plain. And I think that we can't risk doing something which is not typical of the real open ocean. And typical means a rough relief.
But it seems to me when you get all done and you don't understand what happens there, You're going to say, well, let's go over the flat topography.
Well, where is there? You mean over the rough topography or in the first 1,000 meters?
Right. If there's anything you don't understand, you're going to end up saying, well, let's go do another experiment over the smooth topography and wish you had done it to begin with.
I think we should put it here over the rough area. And the reason for this is that, well, we know, or rather we think we know, that the finer scale features down near the bottom tend to disappear as we come up. And this should be typical of the whole ocean.
There is no such thing as a typical piece of ocean. Every piece of ocean is different.
Yeah, but my piece of ocean out here is more typical than your piece of ocean.
We'll have to have a vote on that. Certainly, a flat bottom is more typical of theoretical oceans than rough bottom oceans.
I think, gentlemen, I have a proposal to make. I suggest that we compromise. Why don't we just put it there? And then on this side, Carl's satisfied, and on this side, we can really get our statistics.
But maybe nobody's going to be satisfied with that compromise.
One of the awful things about a compromise is you neither get A nor B.
But we did compromise after studies of the differences between flows over smooth and rough terrain. Between the southeastern coast of the United States and the island of Bermuda, a piece of test ocean less than 400 miles in diameter was finally selected. It's a small piece of ocean compared to the size of the Atlantic, but a large enough area to contain a few eddies. And then at a meeting in Bermuda, we had to decide just how we were going to go about placing all our instruments in that one piece of ocean at the same time. There were problems.
But there are certain parts of this program that have to occur at the same time. And we ought to draw vertical lines through those, where, you know, where the profiles or things like that. So let's try to build a diagram up and try to identify troubles, because I think there are some troubles, notice. For example, you're putting the floats out on a small scale.
Oh, I'm sorry.
Before the moorings are out, even on the large scale. No, I put the floats on the large scale after the moorings are out on the large scale.
Well, they're within 100 kilometers. That was the information diameter of 100 kilometers. I'm sorry.
At a radius of 100 kilometers?
100 kilometers. Yeah, I mean, I'm sorry. This should be out here a little far.
Well, it should be out to 100 maybe. Or up, yeah, go ahead. Yeah, scratch it and make it right.
It's out here someplace.
Gosh, these chief scientists are going to make a botch of this thing when they get out there.
As we prepared to set out, each of us had his own thoughts, his own doubts, and hopes about what we might find.
Well, let's say this. I would be very glad if after the whole thing were over, we came back and felt that we really had a picture of just what was going on in that little spot of ocean. That is, after we have the results in, if we're able to describe the properties of the flow, a simple high school description of the structure of the flow pattern that we see, and one in which we're confident, I think I'll be happy, I'll be satisfied. I have a very modest goal. Now, if we can do more than that, fine.
Hopefully understanding what makes, if you wish, weather in the sea. What are the responsible eddies, or whatever you wish to call them.
There's no question we'll find eddies of various scales and sizes. These, we know they're there.
Or, I mean, conceivably, it could be completely stationary. Just very little motion and none of the pattern that we're looking for.
But after all, that's what we're doing it for. If we knew what the answers were, why would we be here?
Well, I have nightmares of not getting our instruments back.
The pressures are really very immense, and when one adds up the combination of pressure, the corrosive effects of seawater for prolonged periods of time,
and accidents and bad weather, and
attempts by large animals, whales or sharks or swordfish, all of which are known to dive to these depths without any difficulty.
Somebody could come along, pass the central mooring and say, I wonder what that is, and try to drag it in and see what was hanging below the mooring. And except for a little sign that says, please keep off.
Well, the most likely failure, I think, aside from a real catastrophe where you don't get any measurements, would be that we'd get a lot of measurements and we couldn't make any sense of them. And that's very possible. That could happen.
Our ignorance is so great that we're going to miss it entirely. We're going to try to catch a whale with a kitchen sieve.
We may just have got it wrong. And if we're wrong and the real eddies are only half the size we think they are, we're going to come back at the end, and I think I'll go to South America.
In the spring of 1973, after 4 years of talking, planning, testing, arguing, and worrying, we put out to sea to try to find something that no one had ever found before, a deep sea storm. To handle the problems that might occur at sea, we had a ship-to-ship communication system, as well as a hotline center in Bermuda. And so we were still in touch with each other, even on board ship, for more talking, planning, arguing, and worrying. After 3 days steaming, we reached Mode Waters, which looked no different from the rest of the Atlantic Ocean. I'm not an awfully adventuresome type of person who gets a great deal of pleasure out of going to sea, but I do like to play some kind of an active role in finding out how the machinery of the ocean works. I'm sure there's some kind of a simple explanation for the eddy-like motion, and I'd like personally to find out just what it might be. My approach to oceanography is to try to ask the simplest possible questions, and one of the oldest and simplest ways to ask questions about the sea is to take water samples and find out how warm and how salty the ocean is at different depths or layers. We'll be collecting water samples on all of our 6 ships. We're not trying to catch an eddy in a bottle. If there are eddies around, they're much too big to fit into a bottle. What we are trying to do is to get a 3-dimensional picture of the temperature and salinity layers in the Mode area, to map out the lines of equal density along which the water ought to flow. There have been hundreds of thousands of deep water casts in the short history of oceanography all over the world. Temperature and salt readings are not only the traditional measurements of the seas, but also a way of life, shared by oceanographers of all nations. In the Mode area, we have American, British, and Russian oceanographers reading deep-sea thermometers.
Температура 24,58. 24,58. 24,52. 52. 23,6. 23,24. 27,5. Его номер 116.
25.7 and 363. 3.23 at 25.0. 25.0.
God, this is impossible to read.
While the ships, the individual instruments, and the language may be different, the information can be exchanged and used by all as a common description of the sea. While we're taking temperature and salt readings by the old handmade way of doing oceanography, we're also now using new instruments which do the same job automatically. The water samples we collect are now just used to set accurate standards for the electronic instruments. Oceanography has changed a great deal in the past few years in other ways. The kind of people who go to sea. The old polar exploring and yachting types have given way to a more representative cross-section of our population, involved in a variety of new occupations at sea, testing, maintaining, and operating electronic instruments and computers. They've helped to change the old oceanography, which was almost wholly a descriptive kind of endeavor, or perhaps a type of geographical exploration, to what it is today, with physical science dealing quantitatively with fundamental laws of nature. If water sampling represents the traditional approach to ocean currents, then current meters and other direct measurements of flow represent the new. Bob Heinmiller, aboard the chain, can describe the complex job of placing current meters up and down and around the mode area.
The first thing we have to put out is the surface mooring. It marks the center of the mode area. Carries wind recorder, some navigation radio beacons, and a flashing light. The central mooring will sit on the surface, the only gear that will be visible in the whole mode area. Everything else will be hidden below the surface. Now, passing ships are certainly going to wonder what this strange-looking object is out in the middle of the ocean, but they'll stay away from it, we hope.
Hold it, Eli.
The main instruments on the moorings are the current meters. The cylindrical case contains all the electronics. At the bottom is the rotor that measures the flow of the water past the instrument. The records of speed and direction are stored inside the meter case on magnetic tape. The current meters are brought back to the surface by these hollow glass balls, each of which can lift up to 60 pounds in water. The balls are encased in plastic casings, which we call hard hats. They're bolted together and they're attached to sections of chain. The whole mooring, topped by a radio beacon and a light, is first laid out on the surface. Since the top of the moorings will be about 1/4 of a mile below the surface, we have to pay out almost 3 miles of glass balls, current meters, and cable for each mooring. We've developed a technique over the years. After the top of the mooring is over the stern, we steam away from it, slowly going upwind. When the mooring is completely strung out, we try to end up directly over the position on the ocean floor that we want the anchor to rest. The trick in all this is timing the operation. Obviously, there are a lot of things that can go wrong. If you work too fast or the ship goes too slowly because of the wind, you can suddenly find yourself with 1.5 tons of anchor on your hands, ready to go, and you're simply in the wrong place. Sometimes we simply have to hang on to the anchor for an hour or so, dragging this 3 miles of paraphernalia behind the ship, trying to get into the right position, and constantly worrying about passing ships, sharks biting the line, or what have you. We've had a few close calls. I'm always a little tense during mooring launch. There are just too many things that can go wrong. It's always a great relief to finally get rid of the anchor and watch it drag the mooring string down into the water. You sometimes wonder whether you'll ever see any of that equipment again. It's a little unnerving in a way. It's difficult to describe just what happens below the surface. We'd have to start with this familiar sketch of the mode area. And then we would have to stretch it in the direction of the depth, way out of proportion to its actual shape in the mode area, in order to see the central mooring in place and the first instrument mooring, the first subsurface mooring, falling to the bottom, pulled down by the weight of the anchor. Well, ship time is a very valuable commodity, and so we work straight through day and night. We have 2 separate crews that alternate putting out the current meters through the mode area on these 17 moorings. I think that one of the key problems in an operation like this is that it's very easy for the guy in the lab or on the ship to lose sight of what it is everyone is trying to do. Superficially, what we're trying to do is fasten instruments together, reel out line, bend cotter pins, navigate to the next position. But none of this is an end in itself. The object of the game, after all, is to learn something about the ocean. Months later, we'll come back and pick up these instruments, and after the data is processed, we'll see just what we found.
We are launching a set of floats called SOFAR floats. These are brand new, handmade instruments that are being used for the first time in mode. My name is Doug Webb, and I am an engineer, an ocean engineer, if you like. This kind of engineering involves building a capsule that can withstand the rigors of the deep ocean, and also an acoustic system that can transform a small amount of energy into an underwater sound that can be heard 1,000 miles or more. Each float is made up of a long tube which contains all the electrical parts and two short tubes which act like organ pipes in that their length is tuned to produce sounds at a particular frequency. In this case, we have tuned the pipes to C below middle C, and the result, oddly enough, is very similar to the sound made by some whales. Each float uses only 1/4 of a watt of power. We could put out 400 floats and have them play a melody on their pipes, all using the same amount of power it takes to light a 100-watt bulb. We will have launched 20 SOFAR floats in the mode area. They have no connection to the ship, to the surface, or to the bottom of the ocean, and are entirely free to be carried along by the deep currents. To the extent the ocean is variable, each float will follow a separate course. Ready to launch in air, a float weighs about half a ton, but on the surface of the water, it weighs only 6 pounds. It settles slowly, very slowly, weighing less and less as it goes down, until about a mile below the surface it weighs nothing at all and is neutrally buoyant, just like a constant altitude balloon floating in air. The floats take about 1.5 hours to reach their depth of 5,000 feet. Each float transmits its own slightly different sound pattern, which lasts for about 2 seconds every minute of the day for the next 4 months. The signals from the floats sound like a short blast of a foghorn. We call it a pong to distinguish it from the ping made by the floats used by John Swallow. The pongs can be monitored aboard ship to see if all is well, but the floats are not tracked from the ship. We operate 4 shore-based listening stations to find out exactly where the floats are traveling in their journey with the ocean currents. The floats measure the same motions as the current meters, but in a different way. The float stays with a body of water, while a current meter measures the flow past one point. The current meter might see an underwater storm from a fixed point as a slowly evolving, passing event, while the float, caught up in the storm and carried inside it for months, would see the storm in quite a different way. The SOFAR floats are not the only floats in this area. They are pleased to have their British cousins, the Swallow floats, working alongside them. John Swallow is aboard the Discovery.
We're running quite a different operation now from what we did on the old Aries 15 years ago. We can track and keep up with 18 floats at a time, whereas on the Aries we had trouble keeping up with 6. The tracks themselves look pretty confusing. They look like a number of drunken insects crawling about all over the plotting sheet, but this is really what we want to find, what the water's doing. We still track the floats from on board ship as we did before, but now the floats have transponders in them, acoustic transponders, which reply to signals that we send out from the ship. And that, in effect, only turns the floats on when we send commands from the ship, and it's much more economical in power.
Now, we've got nothing on channel 3, no floats in channels 4 and 5 at the moment. Right. Channel 6 we have, and that's 5, 6,
7.3.
7.3.
And a difference of 1.12.
1.12. Float depth?
Float depth on that one's 500.
Right.
Sometimes in a free moment, Jim Crease and I talk about the months we spent on the old Aries chasing floats around the ocean.
Well, that was really because we just had that simple idea of the mean circulation being very sluggish, and that there wouldn't be anything else there except the mean circulation, and that if we had speeds of only a few miles a month, that we'd be able to do it, and we would have been able to do it with the floats that we had, but it just turned out completely different. And I think that was the really surprising thing that we were able to see from the Aries observations, even though they were a pretty bad sample of what they were. They did at least reveal that it was completely different from the preconceived idea that we had before. So that's really one of the reasons why we're doing this now.
And that's one of the main reasons that we're all doing this now, putting out current meters, floats, and instruments on the bottom. Jim Baker can describe the bottom instruments.
Our instruments are like barometers, which sit on the floor of the ocean to measure the shifting weight or pressure of the ocean above. We hope that we can use the highs and lows of ocean pressure to make maps in the same way that weathermen use the highs and lows of atmospheric pressure to describe weather systems and currents. But we need greater accuracy. We have to measure the addition or subtraction of only 1 or 2 inches of water at a depth of over 4 miles. To do that, we use a quartz tube as a pressure sensing device. As the ocean pressure changes, however slightly, the tube shrinks or expands, and the end of the tube rotates. That turns a mirror, which reflects light to a photoelectric cell. The amount of turning is recorded in the instrument. Each of the components has to be protected in a heavy casing in order to withstand the pressure of more than 8,000 pounds per square inch. If the instruments can really see the small changes of pressure that we expect, then we'll be able to decide if the currents inferred by the pressure gauges agree with the current meters that are moored near the bottom. Also, we'll find out if the 3 kinds of bottom pressure instruments that are being placed in the mode area agree with each other. It's the interaction not only of people, but also of instruments that makes mode an exciting experiment. We have to learn about the technology at the same time we learn about the ocean currents. With navigational aids like LORAN and satellite navigation, we can place our pressure gauges within a few hundred yards of where we want them. We don't know if any of them is going to be accurate enough to give us the slight residuals or differences that we have to have in order to infer ocean currents and ocean weather.
With instruments on moorings, others floating through the middle of the mode area, and still others sitting on the bottom, it would appear that we have covered the full range of possibilities. But we also have instruments that go from top to bottom, called profilers. Tom Sanford's profiler measures currents continuously in the whole water column. An advantage of profiling is that unlike some of the other experiments, the results are immediately available. It is possible to look at the numbers right away and then change the experiment as you go. Another kind of profiling is being done from an airplane by Bill Richardson. He is trying out a new method of measuring ocean currents using airplanes to drop probes. The advantage of an airplane is the number of miles he can cover. Time is the key to this operation.
Ready to drop
the time the probes are dropped and the time that floats inside the probes are released.
On course. Stand by for drop. Release.
Off the time.
After the probe sinks below the surface of the water, the first float is released and gives off a green dye. The probe itself continues down to the bottom of the ocean. After it hits the bottom, other floats are released at timed intervals. They also give off green dyes. A second plane then flies over the drop area and photographs the green dyes on the surface. The distance between the dye spots are easily measured and can be translated into currents from any depth in the water column to the surface.
I haven't brought any instruments to sea, and as I said, I'm a theoretician, and this is my first oceanographic cruise of any kind. I was somewhat seasick the first few days, even though the weather was good. Ship can be a very isolated place. A 300-foot platform is your whole world. I don't think I could bear this for very long periods of time. And even some rough weather would be a relief. My job at sea is to stand one of the 3 watches making hydrocasts, or water catching as Henry might call it. I've begun to feel like a bona fide seagoing oceanographer, even though I might not look like one. As far as my theoretical work is concerned, what I can do at sea is to get a first look at some of the data that we're gathering. The mass of information is really overwhelming. When I sit back and look at all the numbers we're collecting, I wonder whether we're being very brave or very rash. I hope that by the end of this experiment, the reputation of the theoretician won't be 10 times worse than it is now. The guy who actually collects the data, that is the experimenter in charge of each specific project or instrument, gets the first crack at it. But then it's rapidly shared by all. This is one of the few occasions in oceanography when everyone has joined in this way. And also one of the few times when theoreticians like myself are in on the design and planning of the experiment, as well as the operation.
This is the RV chain back to the researcher. We have found a very strong, unusually strong current from 800 meters to the surface. Since you will be coming this way in a few days, would suggest you take some extra density stations in this area. Over.
Roger, Alan. We would be delighted, I say again, delighted, to give that area an extra look. Over.
Bermuda CW, Bermuda CW. This is the research vessel chain, the RV chain, to the hotline center. Over.
Bermuda CW to WEML, the research vessel chain. Go ahead, please. Over.
Good afternoon. We have a message. Text as follows. Ship has hit submerged object. Stop. Tentatively identified as large log. Stop. Appears to have damaged tail shaft. Port screw inoperative. Stop.
That is affirmative. That is affirmative. Also, you might be interested in knowing that the Discovery hit a log last night, too, but apparently did not have any damage. They said it looked like a forest floating out there. Over.
Oh, good morning, Mode Radio. This is the Royal Research Ship Discovery.
The computer engineer has analysed the computer fault and came to the conclusion we required integrated circuit part SN74H04N.
Okay, Kilo India Echo Alpha, we'll try to get some replacements for you. We will try to find replacements for you.
Roger that.
Roger that. The aircraft circling your ship is Nova Air Mode. They could not find the chain for their experiment, and they will now drop near you. How on that, please? Roger. I don't know what's the matter with their homing equipment, but they felt they needed to be near somebody, so they picked you. I copied at Mode Center last night. A large unknown ship was seen at position of the surface marker mooring. As chain approached, the ship steamed off, stopped. The buoy cannot be located by radar. ADF. That's a very strange phenomenon. Roger that. Bermuda CW, clear with the chain.
With all the trials and a huge effort by hundreds of people, we put out a full array of all the instruments that can measure deep ocean currents. Related experiments going on in the same piece of ocean at the same time. And now that we have laid them all out, and 4 months have gone by, we've got to try to get them all back again. Sound signals from the ships to the instruments tell them to drop anchor and come back home.
I've got the 2 cables switched right.
Right, but it's still the reading is erratic. It goes anywhere.
You think they're just flipped over when we switch those cables?
Well, at least that's the way it worked the other day.
It looks about right for letting her go, George.
Right. Anytime.
Okay. See, that's release command 1. Okay, here she goes.
Yeah, 1 kilometer exactly. 326. 726 Zulu.
She's released.
Bridge. Yeah, the release as far as she's on the way up. We should get the radio in about 3 or 4 minutes.
Roger. Okay, I'll try to reply finger at level 5, I guess.
We triggered this thing. We're not getting any reply pinger from it. It looks as though it might have released, so would you keep an eye out on the starboard side for us? I haven't got any radio signal from it yet.
Okay.
Judging by the return, I think it looks aft because the return is very weak. 3.25 was our last range, and the bearing appears to be pretty well dead ahead.
Bridge 400 meters dead ahead.
Okay, we have it visually.
Yeah.
290.
Midships.
Midships.
Right 5.
Right 5.
Midships.
Midship.
Watch out.
Takes about 5 minutes for the first glass balls, the ones that are at the very top of the mooring, to hit the surface. At the lower end, takes about an hour for the entire mooring, all the wire, the glass balls, the instruments, to reach the surface. A whole hour to come 3 miles straight up through the water. As the instruments come aboard, one of the first things we look for is to find out whether they're still working and relatively intact. If they have any bubbles, little jets of water coming from inside the case, or if they're a lot heavier than usual, we know right then we've got a problem. In order to keep the decks clear, the float clusters have to be taken apart as they are recovered, and the balls are stored in baskets on deck. The ship is pretty crowded on this particular operation. We wind the wire on reels, or in case of small, short shots, we coil them for storage. In spite of the care and recovery, a lot of the wire comes up tangled. It gets tangled on its way to the surface, and as the mooring is sitting on the surface after we release it. The thing to keep in mind is that the wire is expendable. The main thing is to get the meters back. That's where the data is. Sometimes, in spite of all the machinery, you reach a point where, you know, a couple of people got to reach out there and start pulling and hauling. I mean, there's people who've been known to lose fingers that way, and I once made a rule against doing that. And it simply didn't work. I found myself doing the same thing. You get out there, and there comes a time when it really comes down to the muscles and the will of a few people to get the gear aboard. A few meters were flooded by small leaks in their cases. At the huge pressures in the deep ocean, even a tiny leak can be disastrous. Seawater is very corrosive, of course, and just destroys the electronics. The inside of the meter just gets eaten up very quickly. We can usually save a few spare parts if we hose them down with fresh water immediately after we open them up. That's kind of an agonizing process. You've got $8,000 worth of electronics, and here you are running a garden hose on it. But it's the only way to save part of it. We were pretty lucky this time. Almost all of the meters came back intact.
The floats have small ballast weights that are also released on command by sound signals from the ship.
We bring the ship close to the estimated float position and then start searching. The problem now is to see the tip of a 12-inch tube in the open ocean.
Okay. Oi, port bow!
We depend entirely on the considerable skill of the ship's personnel to sight the float, to bring the ship alongside, to attach a line to it, and to bring it aboard. It is a tricky job even in a calm sea, like threading a needle with a 16-foot pole. The float rides very low in the water and is difficult to see. This fish doesn't want to be landed. The rope pickup loop is too small, and if I had a chance to redesign the float, it would be much larger. That would certainly make many of the seamen happier.
Yeah, you got it. The other hook.
All of our efforts at sea all exploit an oceanic phenomena that sound travels long distances through the ocean. It is very easy to get caught up with this technology and engineering, but our real purpose is to improve our understanding of deep ocean circulation.
The anchor on Baker's bottom instrument is the tripod itself. Again, a sound signal sets off a charge and releases the instrument.
We tend to worry a bit while the instruments are out, so it's a real joy to spot them when they reach the surface. We grow attached to them after long periods in the laboratory, learning their idiosyncrasies. In fact, some of our oceanographers even name them lovingly after their wives. The main point is that we're very interested to know what they have recorded while sitting down there in that quiet darkness. If all works properly, we'll have 4 months of records inside, and our investment is intact. Each of the instruments represents a good part of our annual budget.
Take them down.
Right. One part of the search is over. The measurements have been made and recovered.
Pull the string. No, you pull the string. That's what we got it on there for. Here we go. Woo! Hey!
Who hasn't signed it?
Quite a few people. We'll have to get them afterwards.
At least it's down where they can get at it.
You can put their X's.
That shack with the seat, though, you can move it. Up, get close up. There he is. Down by the basket. He's got a yellow shirt on. He's got the dog.
No, he's got a dog with him.
For Christ's sake.
I didn't recognize you in the front of a new hairdo.
Daisy.
Everybody's had their haircuts. Except Daddy.
Yeah.
Now another part of the search begins. The measurements, for the most part, have been stored on magnetic tape inside the instruments. The tapes are fed into computers, and the information is worked up into a number of forms: charts, maps, graphs, computer images. When all the data has been summarized, the scientists can synthesize the results into a meaningful statement of conclusions. A meeting was held in November, almost a year after the meeting in Bermuda, at which we compared and presented our results. Again, we can call on the oceanographers to tell their own versions of victory, defeat, difficulty, and discovery.
We made about 5,000 miles of tracks measuring currents from the airplane. Current measurements about every 5 to 10 miles.
We made about 70 profiles.
About 800 density stations during the course of the experiment.
The surprise from our work is that the sea bottom instruments should measure a pressure which looks very much like the atmospheric pressure.
Now, there have been some disappointments too.
We found that subtracting the two stations and getting that small residual from a residual, that fluctuation was not sufficiently large to be comfortably above the noise level of the instruments.
It's clear that we're not going to get all the comparisons we would have liked between the current meters and some of the density data.
We did lose some. They didn't come back to the surface for one reason or another.
In terms of the program as a whole, there was enough duplication that none of the instrument failures denied us the ability to look at basic things that we wanted to.
Our principal success to date is that we have definitely found what we were looking for, a mode eddy.
It's really there. We did catch one.
Which, by more or less good fortune, I guess, appears to have been reasonably well centered within the experimental array area.
But it had brothers and sisters, other pressure centers, other eddies that were defined in the outlying region.
And we plotted it up, and there, actually visible, were the eddies that all this talk had been about for the last year.
What we were able to see for the first time was a deep ocean storm, a developing weather system with changing temperature, pressure, and currents. The dark highs and lows are the eddies, with the water swirling around them. Fortunately, a high-pressure area developed in the center, a central eddy, which revealed some of the main features. A changing shape, roughly 80 miles in diameter, with speeds that are 100 times faster and stronger than the mean circulation of the deep Atlantic Ocean. Compared to an atmospheric storm, it may be slow, but it has the massive weight of the water behind it, which gives it more energy than a thunderstorm, and it lasts 1,000 times longer. These eddies must be all over the ocean, the weather of the deep sea. And I think that we found something else, a way to work together without giving up our individual freedom to do what we want to do in our own way, each contributing his individual skills to a common goal. We placed a number of different instruments in the same piece of ocean at the same time, and the results taken together seemed to be much greater than what each of us might have done in his own piece of ocean, in his own time.
Well, I think we really would have liked to have seen more of the full life history of an eddy. We only saw a short period of the life of an eddy, and we don't know whether it was a young eddy or an old eddy or a sick eddy.
But the big questions, the real reason for our effort in this experiment and for our future work are why and how. Why are the eddies there, and how does eddy energy control the ocean circulation? We now have a brief view of the currents and the storms in one small region of the ocean. What we'd like to know is how the whole ocean moves and behaves the way it does, so that we can couple the circulation of the ocean to that of the atmosphere to understand the changes in weather and climate they jointly produce.
And so the next challenge is to try to discover where eddies come from and where they go, by looking at a wider expanse of ocean for a longer period of time. And this will require a larger group of oceanographers from the United States, the Soviet Union, the United Kingdom, and other nations of the world who will join in a coordinated effort to better understand the currents whose strange wanderings in the remote deep sea ultimately affect all our lives.